Imagine standing outside on a clear night, tilting your head back, letting your eyes find that brilliant point of light low in the southern sky, Alpha Centauri, the nearest star system to our Sun, our closest cosmic neighbor. And here is what they never tell you in school. It is so far away that if every human being who has ever lived on this planet joined hands and stretched out in a line, we wouldn't even make it to the front door. We would cover barely a fraction of a percent of the distance. That gleaming dot you can almost feel you could reach out and touch. It sits 25 trillion miles away. And the machines we have built, our fastest, most powerful spacecraft, our greatest engineering achievements, would take longer than all of recorded human civilization just to cover half the journey. We think of Alpha Centauri as close. In the language of astronomy, it practically is. In the language of human ambition, it might as well be the edge of forever. If that kind of tension between what we can see and what we can never touch makes your brain come alive, subscribe. We go deeper every week. Let's begin with the system itself, because Alpha Centauri is not what most people imagine. It isn't a single star waiting patiently in the dark. It is a system, 3 stars bound together by gravity, orbiting their shared center of mass in a gravitational waltz that has been going on for billions of years. Long before our own solar system was a swirl of gas and rock, these 3 stars were already dancing. The brightest of them is Alpha Centauri A. It is larger than our Sun, about 10% more massive, 1.5 times brighter. If you quietly swapped our Sun out for Alpha Centauri A one night while everyone slept, by morning, you'd notice something slightly different about the light coming through the curtains. A touch more warmth, the sun a hair wider in the sky. Life, though, would carry on almost unchanged. The seasons would still turn, rain would still fall. Earth would simply orbit a slightly more luminous master. The second star is Alpha Centauri B, smaller and cooler than the Sun, carrying about 90% of the Sun's mass and half its brightness. If you replaced our Sun with Alpha Centauri B instead, Earth would grow colder, the sky would be dimmer, the days a little less vivid. You'd need to migrate your orbit inward to find the warmth. But Alpha Centauri B is still a perfectly ordinary, well-behaved star. A main sequence star fusing hydrogen into helium in its core, stable, patient, ancient. These 2 stars, A and B, orbit each other in a slow ellipse. At their closest, they're about as far apart as the distance from our Sun to Saturn, roughly 11 astronomical units. At their farthest, they stretch apart beyond the orbit of Neptune to 36 astronomical units. They complete one full loop around each other every 80 years. They completed their last orbit around the time World War II ended, and they will finish their next sometime around 2037. If you could stand on a planet circling Alpha Centauri A and look into the sky at night, you would see Alpha Centauri B as a dazzling second sun, far fainter than the primary, but bright enough at closest approach to cast shadows at midnight, bright enough to read by, bright enough to make you stop and stare. Then there is the third member of this family, Proxima Centauri. Proxima is tiny, a red dwarf, just 12% of the Sun's mass, producing barely a fraction of a percent of the Sun's light. If you placed it where our Sun is, Earth would freeze solid, not gradually, not over centuries, but immediately. It is simply too dim, too cool. To get enough heat from Proxima, you'd have to orbit so close that gravity would lock you in place, one side of your world baking in permanent noon, the other locked in eternal midnight. Proxima orbits the AB pair at an almost incomprehensible remove, 13,000 astronomical units, roughly 0.2 light years. At that distance, it takes Proxima around 550,000 years to complete one orbit. The system itself is 5 to 6 billion years old, slightly older than our own Sun. Alpha Centauri was already ancient when the first rocks of our solar system began clumping together in a distant corner of the galaxy. These stars have outlasted everything we would call history, by a margin that makes the word history seem embarrassingly small, and they will outlast us. In 5 billion years, our Sun will swell into a red giant and swallow the inner planets. Alpha Centauri A and B will still be there, still dancing. Proxima, burning its fuel so slowly it barely seems to breathe, will still be shining trillions of years from now, long after every other star in the sky has gone dark. Red dwarfs are the last lights in the universe. They were here before we were. They will be here long after we are gone. And yet, we cannot reach them. Here is the number that matters. Proxima Centauri, the closest of these three stars, is 4.24 light-years from Earth. That is 25 trillion miles. Alpha Centauri A and B sit slightly farther at 4.37 light-years. These are the nearest stars beyond our Sun. Nothing is closer. There is no shortcut, no closer stepping stone. If the entire galaxy were a city, Alpha Centauri would be the house next door, and the distance to that house is 25 trillion miles. People have watched Alpha Centauri for thousands of years. Ancient astronomers in the southern hemisphere knew this brilliant point of light. Ptolemy catalogued it in the 2nd century. Arab scholars observed it. Chinese astronomers recorded it. For most of human history, we assumed it was a single star, just a bright nail of light hammered into the southern sky. That changed in 1689, when a Jesuit priest named Jean Richaud, observing from Puducherry in India, noticed something extraordinary while peering through his telescope. Alpha Centauri appeared double, two stars, not one, close together, orbiting each other. This was a rare find. Binary stars, pairs gravitationally bound and circling their common center of mass, were exciting discoveries at the time, valuable windows into the mechanics of how stars work. Astronomers spent the following centuries carefully tracking the orbit of Alpha Centauri A and B, measuring their positions year after year, watching the slow celestial waltz, calculating the eccentricity and period of the orbit. By the 1800s, they had established the 80-year cycle, and all of this, remarkably, was accomplished without knowing how far away the system actually was. They could measure angles and relative positions, but not absolute distances. That required something more delicate. It required parallax. In 1832, a Scottish astronomer named Thomas Henderson, stationed at the Royal Observatory in Cape Town, South Africa, began making precise measurements of Alpha Centauri's position against the background stars. He was trying to detect stellar parallax, the tiny apparent shift in a star's position that occurs as Earth moves from one side of its orbit to the other over the course of a year. For even the nearest stars, this shift is smaller than 1 arc second. 1 arc second is 1/3600th of a single degree. To put that in human terms, hold a coin at arm's length. The width of that coin spans roughly 1800 arc seconds. Henderson was trying to detect a shift less than one of those, less than 1/1800th the width of a coin held at arm's length. He observed Alpha Centauri for months, made hundreds of measurements, and detected a wobble, a genuine signal. But Henderson was cautious, maybe too cautious. He worried about errors in his instruments, about the atmosphere bending his observations, about all the invisible ways a measurement could quietly go wrong. He sat on his data for years, analyzing and reanalyzing, hesitating to publish. Meanwhile, in 1838, a German astronomer named Friedrich Bessel published the first confirmed measurement of stellar parallax for a different star, 61 Cygni. Bessel's work was meticulous, methodical, bulletproof. He had accounted for every possible source of error, developed mathematical techniques to extract the true parallax signal from the noise. His result was undeniable. When Henderson finally published his Alpha Centauri measurements in 1839, a year after Bessel, he confirmed what the German had shown. Stars were unimaginably far away. The nearest one, Alpha Centauri, was 4.3 light-years distant. Modern instruments, far more precise than anything Henderson had access to, refined that number to 4.24 light-years for Proxima and 4.37 for A and B. Henderson was remarkably close. That discovery changed everything. For the first time, humanity understood the true scale of the gulf separating us from the stars. They weren't lights on a celestial ceiling, close enough to touch if only we could climb high enough. They were distant suns, separated from us by empty space on a scale no one had dared to imagine. That was in 1839, nearly 200 years ago, and we still haven't gone there. To understand what 4.24 light-years actually means, you have to sit with the speed of light for a moment. Light travels at approximately 186,000 miles per second. Nothing in the universe can travel faster. This is not a speed limit we haven't broken yet, like the sound barrier. It is a fundamental law of physics. absolute, constant, non-negotiable everywhere in the universe. When you look at Alpha Centauri on a clear night, the light entering your eyes left that star system 4.24 years ago. You are not seeing the star as it is, you are seeing it as it was. If something happened to Proxima Centauri today, if it flared, changed, went suddenly dark, we wouldn't know about it for 4 years and 3 months. The information cannot reach us any faster. We would keep seeing the star as normal, watching old light arrive on schedule, blissfully unaware. This creates a fundamental isolation. We are cut off from the universe not just by space, but by time. Now think about traveling there. Our fastest spacecraft is the Parker Solar Probe, which uses the sun's gravity to reach speeds around 430,000 miles per hour, fast enough to circle the Earth in 3.5 minutes, fast enough to reach the Moon in 33. But at that extraordinary speed, pointed at Proxima Centauri, the Parker Solar Probe would arrive in approximately 6,700 years. If it had launched when Alpha Centauri's distance was first measured, it would be less than 3% of the way there right now. The Voyager probes, which are genuinely in interstellar space, having crossed the heliopause, travel at around 38,000 miles per hour. At that speed, they would take roughly 75,000 years to reach Alpha Centauri. 75,000 years ago, modern humans were spreading out of Africa for the first time. We had stone tools, fire, and probably some form of language. We had no agriculture, no cities, no writing. Everything that defines civilization, from the first farms to the pyramids to electricity to the internet, has unfolded in the time it would take a Voyager-class spacecraft to reach the nearest star. These timescales are not just large, they are incompatible with human mission planning in any way we currently understand it. The electronics would fail, the power source would exhaust itself, micrometeorite impacts and radiation would slowly dismantle the structure. Long before the spacecraft arrived, it would be silent, a piece of drifting metal, cold and dark, sailing through the void it was meant to cross. So we need to go faster, much faster. Imagine a spacecraft that traveled at 1% of the speed of light, about 1.86 million miles per hour, more than 140 times faster than our current record. Even at that staggering velocity, the trip to Alpha Centauri would take 424 years, longer than the United States has existed as a nation, longer than any nation-state has maintained its current form. You could potentially design a multi-generational vessel, a colony ship carrying thousands of people, a self-sustaining habitat designed to function for centuries. The people who departed Earth would live their entire lives aboard it. Their children would be born in space, grow old in space, and die without ever having stood on a planet. Their grandchildren would inherit a mission they never chose. Their great-grandchildren would be the ones to finally arrive at a destination selected by ancestors long turned to dust. Think about what that means philosophically. Is it right to commit unborn generations to a journey they had no say in choosing? To raise children who will never breathe open air, never feel rain, never see an unobstructed sky? And if something went wrong halfway, a system failure, a food shortage, a disease, a breakdown in the social order that holds the community together, there would be no turning back. No authority to call, no rescue ship to launch, no abort option. Once you leave, you are committed, absolutely and permanently. Even beyond the ethics, consider the engineering. Machines wear out, systems fail. A spacecraft meant to last 4 centuries would need redundant systems for its redundant systems, manufacturing capabilities to fabricate spare parts that haven't been invented yet, and a crew skilled in every conceivable discipline of repair and maintenance. What happens when the genetic pool begins to show stress after generations of isolation? What happens if factions form, if political movements fracture the community, if one group decides they don't want to continue the mission their ancestors chose? On Earth, when societies fracture, people can leave. On a generation ship, there is nowhere to go. Now, accelerate to 10% of the speed of light, roughly 18.6 million miles per hour. The trip shrinks to 42 years. Still a long time, but within a single human life. You could board the vessel in your 20s and arrive in your 60s, old but alive, with your own eyes seeing what you set out to find. This feels almost imaginable, but the physics becomes ferocious. At 10% of light speed, a single grain of sand, 1 gram of mass, striking your spacecraft would release energy equivalent to roughly 43 tons of TNT, about 3 times the energy of the bomb that destroyed Hiroshima, from a grain of sand. You would need shielding so massive it adds enormously to the mass you need to accelerate, which requires more fuel, which adds more mass. The rocket equation compounds against you at every step. Current chemical rockets achieve barely 1% of their mass as useful payload. For every kilogram of spacecraft, you need 99 kilograms of fuel. For interstellar velocities, those ratios become grotesque. And there is the radiation. Astronauts on the International Space Station receive around 50 to 200 millisieverts of radiation per year, 10 to 100 times the dose an average person receives on Earth. And the ISS still benefits from the shelter of Earth's magnetic field. On an interstellar voyage, there is no magnetosphere, no planetary shield. Cosmic rays, high-energy particles accelerated to near light speed by distant supernovae, stream through space in all directions, all the time. Over 20 years, the accumulated dose would far exceed any threshold considered safe for biological tissue. Shielding helps, but shielding is mass. Mass requires fuel. Fuel requires more fuel. Then there is the psychological dimension. Imagine 20 years in the same corridor, surrounded by the same faces, staring out at a sky that never changes. The stars, even at a fifth of light speed, are so distant that the view out the window barely shifts from month to month, let alone day to day. There are no landmarks, no sense of forward motion, just an endless, featureless dark, with a slightly brighter point of light ahead of you that only brightens if you compare images separated by months. Isolation studies conducted on Earth, modeling long-duration missions, show that even after just months in confined spaces, people experience elevated depression, increased interpersonal conflict, declining motivation. We have no data at all on what happens to human beings confined together for 20 years with no escape, no outside intervention, no possibility of early exit. We can screen for psychological resilience, but 20 years changes people. Circumstances change. What begins as a perfectly calibrated crew can fracture under the slow, grinding pressure of infinite proximity. And even if the crew holds together, even if the spacecraft holds together, there is another problem that has no solution: communication with Earth. The moment you leave, the conversation begins to lag. After 1 year of travel at 10% of light speed, you are about 0.1 light years from Earth. Messages take 5 weeks each way, 10 weeks round trip. Slow, but manageable. After 10 years, you are 1 light year out. Messages take a year each way, 2-year round trips. The news you receive from Earth is already a year out of date by the time it arrives. After 20 years, round-trip communication takes 4 years. You are farther from Earth than Proxima Centauri is. The signals are weak. The content is increasingly irrelevant. By the time Earth hears about a problem on your ship and sends advice, the problem has already resolved itself, or become a catastrophe you have long since had to handle alone. You are, in every meaningful sense, on your own. And when you finally arrive, after a century of travel for a slower ship, you transmit word back to Earth. The message takes 4.24 years to arrive. Earth responds. That response takes another 4.24 years to reach you. By the time you receive congratulations on your arrival, you have been at Alpha Centauri for over 8 years. The people who built your mission have grown old or died. Governments that once cared about your journey have long since moved on to other priorities. Your transmissions home are archaeological artifacts arriving in the future, and your children, born on the ship, raised in this strange nowhere between stars, have never seen Earth except in videos. To them, Earth is mythology, the ancestral homeland, impossibly distant, unreachable. Their grandchildren, born at Alpha Centauri, will know Earth as we know ancient Babylon. They will study it as history, not home. This is what interstellar colonization actually means. Not the expansion of humanity, its permanent, irreversible fragmentation. Communities isolated by distances that no communication technology can bridge in any human-feeling timeframe. Drifting apart culturally, linguistically, socially. Different peoples sharing a genetic origin and nothing else. Once you go, you do not come back. Neither do your descendants for countless generations. You have not extended the human family, you have split it, cleanly and forever. Let's step back and look at our actual position in this cosmic neighborhood. The 5 spacecraft we have sent on trajectories that will eventually carry them out of the solar system, Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons, are not aimed at Alpha Centauri. None of them. They are drifting in entirely different directions, heading toward various points in the sky that have nothing to do with our nearest neighbor. Voyager 1, the farthest human-made object ever built, currently sits about 15.8 billion miles from Earth, roughly 159 times the Earth-Sun distance. It crossed into interstellar space in August 2012. It is traveling at 38,000 miles per hour, and it would take about 75,000 years to reach Alpha Centauri if it were aimed that way, which it isn't. The Voyagers are not going anywhere in particular. They will drift through the galaxy forever, carrying their golden records, silent ambassadors from a civilization that built them and then forgot them. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. It will not stop. It will just drift past. Perhaps, billions of years from now, another intelligence will find one of these craft drifting cold through the dark and piece together that a species called humans once lived on a small planet orbiting an unremarkable star. But neither Voyager will ever see Alpha Centauri. The Voyager probes are about 20 light-hours from Earth. Alpha Centauri is 4.24 light-years. That means the farthest thing we have ever sent into space is 0.0023 light-years out. We have barely crossed the driveway. The nearest star is 1,843 times farther than we have ever reached. There are about 14 star systems within 10 light-years of the Sun. Most of them are red dwarfs, small, dim, barely visible even through telescopes. The list reads like a directory of unreachable neighbors. Barnard's Star at 6 light-years, Wolf 359 at 7.9, Lalande 21185 at 8.3, Sirius at 8.6, Luton 726-8 at 8.7. These are the closest things in the universe to us. If we cannot reach them, we cannot reach anything. And beyond 10 light-years, the numbers grow daunting fast. Roughly 71 star systems within 20 light-years, around 200 within 30, about 14,000 within 100. The Milky Way contains somewhere between 100 and 400 billion stars. The galactic center is 26,000 light-years distant. Andromeda is 2.5 million light-years away. Each step multiplies the impossibility. If 4.24 light-years is already this hard, 2.5 million is not a different category. It is a different universe of difficulty. There are people working seriously on this problem. They have been for decades. The most discussed recent mission concept is Breakthrough Starshot, announced in 2016 with support from physicist Stephen Hawking and funded by entrepreneur Yuri Milner. The idea is elegant in concept. Build thousands of tiny spacecraft, each barely the mass of a few paperclips, attached to ultra-thin reflective sails just a meter across and only a few atoms thick. Then, from Earth, focus a massive array of lasers, perhaps 100 gigawatts of combined power, onto the sails. In minutes, the laser pressure accelerates these tiny probes to 20% of the speed of light. Then the lasers switch off and the probes coast. No fuel, just momentum, carrying them silently across the interstellar void for 20 years until they reach Alpha Centauri, snap whatever data they can and transmit it back. Total mission time from launch to receiving the data, roughly 25 years, a single generation. The engineers who designed the mission could live to see the results. It is a beautiful idea, and the hurdles are enormous. Building the laser array alone would likely cost tens of billions of dollars. Each laser must be perfectly synchronized and aimed. The atmosphere distorts light, so the array would probably need to be in orbit. The sail material must be both transparent enough to reflect virtually all laser energy without absorbing heat, and strong enough not to tear at 100 gigawatts of pressure, two requirements that are currently in fundamental tension with each other. At 20% of light speed, any dust grain is a bomb. The probes are so small and light that even a single impact from interstellar debris could obliterate them entirely. Breakthrough Starshot's answer to this is numbers. Send thousands of probes and accept that most won't make it. A shotgun approach, quantity over perfection. And even the survivors, flashing through the Alpha Centauri system at a fifth of light speed, would spend only a few hours in the vicinity before disappearing into the void beyond. Years of travel, hours of science.